Have you ever stopped to think about how the water from your tap gets so incredibly clean? It's not magic. It's actually a really clever engineering trick that's happening 24/7 behind the scenes. Today, we're going to pull back the curtain on one of the most important yet least known concepts in water treatment, the surface overflow rate.
Okay, so let's just jump right in. Picture a massive tank, like millions of gallons of murky water. How on earth do you get all the tiny suspended gunk out of it? It seems like an impossible task, right? Well, it turns out the solution is surprisingly elegant, and it's at the heart of everything we're talking about today.
So here's how we're going to break it all down. First, we'll define what surface overflow rate even is. Then, we'll get into a really cool analogy, the settling speed race. After that, we'll look at the simple math behind it, see how it's used for both design and day-to-day operations, and finally, explore why the type of gunk we're removing makes all the difference.
All right, let's get started. First things first, what exactly are we talking about when we say surface overflow rate?
Think of the surface overflow rate, or SOR, as the speed limit for water inside a giant settling tank. If the water moves too fast, it's just going to wash away all the particles we're trying so hard to remove. But if it's too slow, the whole system gets backed up and becomes super inefficient. It's all about finding that Goldilocks speed. Just right. You might also hear it called the hydraulic loading rate, or HLR, by the way. Same thing, just a different name.
Now, this whole speed limit idea is where things get really fun. The best way to understand SOR is to imagine it as a race, a constant battle that's happening inside every single one of these water treatment tanks.
And in this race, we've got two main competitors. In one lane, you've got gravity. It's constantly pulling every little particle downwards, trying to get it to settle at the bottom of the tank. And in the other lane, you have the forward flow of the water. That's our SOR, which is trying to sweep those exact same particles horizontally right out of the tank. It's a non-stop tug-of-war. So, here's the crucial part. The winner of this race literally determines whether we get clean water or not. If the particle's downward speed is faster than the water's forward speed, gravity wins. The particle settles out, gets removed, and we're one step closer to clean water. But if the water wins, that particle gets carried away, making the water cloudy and the whole process less effective. And that is exactly what we need to avoid.
So, how do we rig this race to make sure gravity and the particles win every single time? Well, it's not about luck. It all comes down to a really simple calculation. The first ingredient you need is the flow. This is pretty straightforward. It's just how much water is coming into the tank over a certain period, usually measured in gallons per day.
The second ingredient is the size of our racetrack, the surface area of the tank. Now, this is a really key point. We only care about the top-down area, like a bird's eye view. The depth of the tank, it actually doesn't matter for this calculation at all. It's all about that horizontal space.
And that's pretty much it. You just take the flow, divide it by the surface area, and boom, you have your surface overflow rate. It's that simple. So the final number you get tells you exactly how many gallons of water are flowing over each and every square foot of that tank's surface every single day. This single metric is what gives engineers and operators total control over our settling race. It's incredibly powerful.
Okay, so we've got this magic number, but what do we actually do with it? Well, it turns out that SOR is absolutely critical for two very different jobs: designing a plant from scratch and running it day to day. This is so cool. For the engineers who are designing a brand new water treatment plant, SOR tells them exactly how big their settling tanks need to be to serve a whole city. But then, for the operators running that same plant years later, it becomes a real-time management tool. Say a huge rainstorm hits and the flow of water into the plant suddenly doubles. They use the SOR to know precisely when to open up a backup tank to slow everything down and keep that settling race under control. But here's where we add a final, really interesting layer to all of this. It turns out not all gunk is created equal. The type of solid particle we're trying to remove has a massive impact on the target SOR we're aiming for. You see, we're basically dealing with two main categories of solids. You've got your primary solids. These are the bigger, heavier particles that settle out pretty easily. Think of them like tiny, heavy pebbles. But then you have the secondary solids. This stuff is light, it's fluffy, it's biological, and it is way harder to capture. Think of it more like tiny, waterlogged snowflakes floating around.
And this table shows you exactly how we adjust that speed limit to deal with these different particles. For the heavy pebbles in a primary clarifier, we can let the water flow much faster, between 800 and 1,200 gallons per day per square foot. But for those light, fluffy snowflakes in a secondary clarifier, we have to slow the water way, way down to give them a chance to settle.
And you can really see the difference here on the chart. The average speed limit for those heavier primary solids is significantly higher than for the lighter secondary ones. It all comes back to giving those delicate snowflakes enough time to win their race against the current. So the ultimate takeaway is this: the lighter and fluffier the particle, the slower the water needs to move. A lower SOR gives them more time to settle. And that's why the tanks designed to remove those snowflakes are often so much larger. They need a much bigger racetrack to get the job done right. And this whole thing, this beautiful balancing act between flow and gravity, is happening right now in your city to make sure you have clean water. It's just one example of the incredible, invisible engineering that makes modern life possible. It really makes you wonder what other hidden systems are out there, working perfectly in the background, just to make our lives a little bit easier.